Lecture 29, Real-Time Scheduling, Windows, and Unix. So this isn't a real-time operating systems course, but I want to give you an introduction to the idea, specifically talk about scheduling for real-time systems. But what is a real-time system? Well, it is one that is supposed to respond to events within some wall clock amount of time. This implies that there are deadlines and there are potentially consequences for missing a deadline, right? If you're being asked to evaluate a transaction to say yes or no, there is a deadline. If we miss that deadline, a default decision is taken. There's lots of real-time systems that we're going to talk about as well. Any driver assist systems in your vehicle are real-time systems because them warning you about the oncoming car is not very helpful if it warns you about it after the car has already passed, right? Those kinds of things are not very useful. So they're supposed to respond to events within a certain amount of real wall clock time. And there are deadlines and there are consequences for missing those deadlines. And I think you can probably imagine what the caption is on this picture without my having to say the bad words out loud, right? I think you've got an idea of this. Fast in systems that are real-time is not as important as predictable. Knowing that we're going to make the deadline is more important than what we are supposed to do being done as fast as possible, right? Now, doing it faster does help us meet our deadlines, but it's not the only thing. If real-time systems are of interest to you, you might wish to take some of the later embedded system courses, including the famous computer science trains course. Although Surgeon General's warning, the CS trains course is known to result in high levels of stress, low levels of sleep, and or potential loss of sanity. So thank you for paying attention to this mandatory legal warning. Okay. So we say that a task is hard real-time if a deadline has to be met to prevent an error, prevent some damage to the system, or for the answer to make sense. If the task is attempting to calculate the position of an incoming missile, a late answer is no good. Similarly, if we have a requirement to respond to a request within a certain amount of time after which a decision has been rendered, if we miss it, we missed our opportunity to give input, so what we have to say afterwards doesn't mean anything. A soft real-time task has a deadline that is not, strictly speaking, mandatory. Missing the deadline degrades the quality of the response, but it's not useless. Like a weather forecast or something like that is not as useful if it arrives later, but it may not be entirely useless, right? And so, as you can imagine, if a task is hard real-time, there are two, I'll call them pretty obvious scenarios in which it might not complete before its deadline. Any ideas what they are? Okay, the first is that it's scheduled too late. Like an assignment that takes 2 hours to complete being started 1 hour before the deadline, like success is impossible. So if that's the case, the system will likely reject the request to start the task or maybe just never schedule it to run at all if it does actually get accepted because there's no point, right? Failure is inevitable. There's no way to accomplish the request and therefore we shouldn't. Okay, now the analogy of the assignment breaks down a little bit because it is possible in a way to get some part marks if you do a part of an assignment and you submit the part of the assignment, but let's imagine, if you will, that that's not the case. And yeah, in this circumstance, we're just wasting time, right? Why would we spend effort trying to complete a task that we know for sure is going to fail? Okay, so that's one scenario. Anybody think of a second one? Yeah, the second one is that when we started, completion was possible, right? It was not always impossible from the beginning, but things came up. Stuff happens, right? That's the polite way of saying it. And that is for whatever reason, right? Something comes up, other tasks with higher priority have occurred, it's no longer possible to meet the deadline for some reason or another. If that's the case, execution of the task may be terminated partway because, well, again, why waste additional effort, right? The initial effort can't be brought back. Like, you can't undo the work that you've already done. Time is linear in that regard, unless you've invented time travel, in which case, why are we talking about this? But execution of the task could be terminated partway if it's not worth it. Most of the operating systems that we are talking about, like your standard desktop or server Linux, Mac OS, Windows, they're not really suitable for real-time systems because they don't make guarantees about service, right? There's no promise about how long it's going to take to complete a certain thing when you submit it, and that's just reality, right? That's not their purpose. When there are consequences for missing the deadline, then we care. Then we have to do something about it, and so probably we want a different kind of operating system, or at least a differently configured Linux. You'll remember, if you will, the Java garbage collector that we've talked about, and one of the ways that it does the garbage collector is stop the world. That is to say, it stops all program execution, so it can rearrange memory as it needs, and then continue. Well, if that happens at an inconvenient time, while we're waiting to respond to some real-time something, that's bad, right? We do not like that. It is also important to note in Windows, you can set a high priority, and if you right-click on a task and you set the priority, one of the options is labeled real time, but please don't be fooled. That doesn't guarantee that it will actually meet a particular deadline. Okay, so I want to talk about a couple of things related to real-time scheduling, and the first one is timeline scheduling. And if a particular task is going to occur at regular intervals, we would say it is periodic. As the saying goes, all of this has happened before and will happen again. And systems have lots of periodic tasks. Check a sensor, decode and display a frame of video, do the Wi-Fi connection keep alive, all that kind of stuff. It happens at a regular interval. You do it periodically, and it's just a recurring task, right? So a periodic task has two attributes. Number one, tau k, the period, how often it occurs, and ck, the computation time, how long, in the worst case, that the task might execute. And it is important, incidentally, in real-time systems that we almost exclusively talk about worst-case scenarios. We are always interested in figuring out whether or not we can achieve our objectives, even if things go wrong. And it is, the worst case that we care about, because if we're certain that everything is fine in the worst case, then we're certain everything is fine if it's not the worst case. Okay. So, when we have these things, we can calculate the processor utilization of periodic tasks according to the following formula. And it gives us the long-term average of processor utilization, which is to say that it is just the sum for all tasks of their worst-case computation time divided by how often they occur. And if we get a value of u that is less than 1, we're happy. We have, it would seem, enough computation capacity to do what we want. But if it's greater than 1, it means the system is overloaded. If the system is overloaded, we cannot guarantee that we can find a schedule that meets all of the deadlines. Otherwise, we will be able to devise a schedule of some sort that makes it all work. Right? Now again, if we're overloaded, it's not a guarantee that there's going to be a failure to meet the deadlines, because we are talking about worst case scenario. And when we talk about worst case scenario, as I say, we are being pessimistic, and therefore there is the possibility that we're lucky and everything works out fine, or maybe that our estimate for what is the worst case scenario is just like apocalyptic, like it's the worst case for real, but like plus 20 minutes, in which case, yeah, of course our estimates are way above what we'd expect, and we will be able to still make it work in reality. But if not, if our estimates are realistic, then if we're overloaded, we're not going to be able to do it all. Now, if the only tasks in the system are periodic ones, then we create a fixed schedule. And this is what happens for the university administration at Needles Hall when they create a schedule of classes for a given term, right? So given a time and a resource, time being a time slot and resource being a room, they will come up with a schedule for everybody that does the best that they can to have the fewest conflicts. So every Monday, for example, 1330 to 1450, the course SE 350, which you can think of as a process in this regard, takes place in classroom STC 0050, which is a resource. Your actual course and location will vary, of course, from term to term, and the time will be different as well. There's no way to switch between processes midway. We don't make everyone leave the room mid-lecture to allow everybody from another lecture to come in for 10 minutes and then switch back. But ultimately, you can think of resources as rooms being limited. They're like CPUs, and processes are courses. And if there are more requests for room reservations than rooms and time slots available, it means that some requests cannot be accommodated. Right? If there's just too many requests, there's nothing that we can do. We can't make more rooms, at least in the short term, right? If you have a couple $100 million and a couple of years to wait for it to happen, then yes, you can build a new building and call it Math 4 or Engineering 10 or whatever we're up to now, and we can make that work. But that's not exactly a quick process. So for a given term, we should say the number of rooms and things is fixed, and we just have to work with what is presently available. But of course, life isn't always this nice, right? A world in which all the tasks are periodic and behave very nicely it's a very orderly world. And that has its appeal, but it's not always going to be like that, because we will have to deal with tasks that are not periodic, which we will categorize as aperiodic or sporadic. And sometimes it probably makes sense to just call them sporadic tasks, because, do I mean, a periodic task, meaning, a single task that is periodic, or do I mean an aperiodic task, meaning a single task that is not periodic? It's somehow a little bit easier if I call it a sporadic task. That makes it a lot clearer what is intended, and also probably helps the auto-generated captions in the video, and reduces the possibility of confusion. So I'll try to call them sporadic tasks to make it clear what are the ones that we're talking about. We mean the ones that are discussed here. And sporadic tasks, sticking to what I just said, are the ones that respond to events that occur irregularly. So, wild task appears. There's no minimum interval between sporadic events, and therefore it's very difficult to make a guarantee that we finish the first before the next occurs. So, sporadic tasks are very rarely hard deadlines, hard real time. What we'll try to do is schedule them in such a way that they don't make another task miss its deadline, right? But luck can be on your side or it can be against you. If we expect an average arrival of 3 requests per second, that sounds kind of manageable, but there's still a 1.2% chance that you have 8 or more requests that appear within 1 second. And if that's the case, it's unlikely that we can accommodate all of them, right? We'll try our best. We may be able to get some, but not all. But if we are very unlucky, the average does not mean they're evenly distributed, because these are sporadic tasks. So we're going to have to do our best. And sporadic tasks, as I say, sort of have no minimum interval by default, but if they do require meeting deadlines, then, well, we need to guarantee that there's a minimum time between occurrences of the event, right? And if that's the case, then yeah, we can probably promise that we can meet the sporadic tasks as long as they appear with this minimum interval. As we know, sporadic tasks can overload the system if there are in fact too many of them. And if that's the case, we're going to have to make some decisions about what to do. Do we even try? Again, if we know a task will make its deadline, we probably avoid scheduling it altogether. Okay, so these sporadic tasks potentially mess with timeline scheduling. This unpredictability makes it pretty hard to create a simple timetable and follow it. And if we have preemptive scheduling, that is to say we can interrupt what we're doing if something of a higher priority happens to occur while we're waiting or while we're working on it, then we can actually come up with an optimal schedule or an optimal approach for scheduling, let's call it that, that ensures that all tasks meet their deadlines. And these two algorithms that we're going to talk about are referred to as optimal because they ensure a schedule where all the tasks meet their deadlines if that's possible to achieve, not because they are like provably ideal algorithms, that like there could exist no better algorithm. It's not optimal in that sense. So the first one that we're going to talk about is called earliest deadline first, and I'm going to guess it is probably quite familiar to you as a student. If there's an assignment that's due today and one that's due next Tuesday, and as yet another one that's due the week after that, you probably do them in the order of the earliest deadline, right? So the assignment that's due today, you do that first. I mean, you don't have to, right? You don't have to, but it's probably going to be your best bet. And after completing an assignment, right, you will decide what to do is next, and it's probably the next one, but there could be a new one, so maybe something new has arrived in the meantime, and you get on with that. And the task is the same for the computer, right? Choose the task with the soonest deadline. If there's a tie between those two, just choose randomly, or you could use other criteria if they have some other associated data that helps you make a decision. You absolutely can do that. There's no reason why you have to choose randomly, right? It's just an idea. So that's one algorithm, and if there exists a way to schedule all the tasks such that all deadlines are met, the earliest deadline approach will find it. And I emphasize will. It's not might, but will. And it's if another task is executing, this is the part about preemption, with a sooner deadline, the currently executing task should be suspended and a new task is scheduled. And this does mean sometimes that, yes, a periodic task is going to be preempted by a sporadic one. That's fine. These kinds of things are important to making it work. Right? If we don't do what we are supposed to do and drop what we're doing to deal with something more urgent, we won't get the correct results. The other algorithm that's similar to earliest deadline first is least slack first. And no shade on Slack, the app, but I just appreciated, I guess, the opportunity to get to use this image. So Slack has a specific definition, and the definition is how long can a task wait before it must be scheduled to meet its deadline. So if we know that a task has a worst case runtime of, say, 10 milliseconds and the deadline is 50 milliseconds away, if we do the very simple math on this, it says, okay, there are 50 minus 10, 40 milliseconds of slack time remaining. So that means that we have to start the task within 40 milliseconds if we want to be sure that it completes on time. That doesn't mean that we necessarily want to wait 40 milliseconds before we start the task. Students may operate on a different basis. In my 2A term, I was lab partners with a guy who actually did have that kind of attitude. It is completely the opposite of my way of doing things. So I found it stressful, and it's a prompt now when someone approaches me or a group approaches me to talk about their capstone design project. It's a prompt for me to ask them questions about their working styles. Right? But we don't actually wait the 40 milliseconds before starting the task. We would prefer to start and finish tasks equal as fast as we can, all things being equal. But it does give us an indication of which are the tasks that are in the most danger of missing their deadlines, and the ones that are in the most danger of missing their deadlines are the tasks that we should start as soon as we can. Now, either one of these algorithms is going to be optimal, as we discussed earlier. That is to say, we can be certain if we choose one or the other for a real-time system that we will be able to find something that makes it work if it's possible to succeed, right? No guarantees about it being possible to succeed if we get too many tasks in too short of a period of time, but we have a hope. We'll leave off the discussion about real-time operating systems at this point. We're going to talk now in the next topic about sort of what happens in commercial operating systems, talking about like Unix and a little bit about Windows as well.